All right, so hello and welcome. Here we are again, another question. This is going to be the n queens problem. This is another kind of a classic problem you'll see from time to time. I think we'll just get right into it. So, alrighty, yeah, this shouldn't be too bad. We'll see how this goes. I have an idea already for this also. So n queens, the n queens puzzle is the problem of placing n queens on an n by n chessboard such that no two queens attack each other given integer n. Return all distinct solutions to the n queens puzzle. You may return the answer in any order. Each solution contains a distinct board configuration of the n queens placement where q and dot both indicate a queen in an empty space respectively. Explanation, there exist two distinct solutions to the four queens puzzle as shown above. N equals 1 is just q, and they give you the two solutions for the first one. N is 4, and n is going to be between 1 and 9. So this is pretty straightforward, and I'll explain the solution though. It's what they call, it's another DFS kind of a question. One different, so we're actually going to, the next problem there's two more problems we're going to solve today. So there's this problem. There's another problem, which is the same problem, but using the number of solutions rather than giving all the solutions. And then we're going to take another question after that. So the way you resolve this one, what you're going to do is it's going to be just like we did with the Sudoku problem. For each row, you're going to select a queen position that's possible of the possibilities. And what you're going to do is you can use, it's not going to be a bit set we're going to do. For each row, it's going to be a vector of integers, right? So sort of a vector of vectors, I guess. Each row will get another vector, and that vector is going to be integers, and it's going to be each column will have another integer. And that's going to be, so initially it'll be 0. The rows themselves, we don't have to affect each other. We actually only need to affect downwards. So we're going to set the queen for that row based off of the zeros that are there. Anything that's a 0, we can set we can set a queen there. We can actually, instead of doing zeros, we could just do -1. And anything that's a -1, that's fair game, and we flip that to a 0 to represent that there's a queen there. And then we would say, recurse. I'll explain what the recursion does in a moment. There's some more processing before recursion, and then after the recursion, we're going to flip that back to a -1, and also reverse the operations that we performed before the recursion, and that's pretty much that simple. The recursion, we're going to update. We're going to go to the next row. So there's a row variable, and in addition to the state that we have, which is the rows, and yeah, if that particular configuration, if any of those, if that recursive configuration is true, then we would, there's a base case actually, so we don't even need to have it true, we could just recurse. There's a base case that if it's true, then we'll take our row configuration, process it, convert it back to a vector of strings as needed, and then push that to our, now hold on a second, is that? Oh, that's interesting. So, yeah, okay. So we'll actually convert each row to a string, and then that'll create a vector of strings for our representation, and then push that to the return value, the return vector of the boards that work. So the processing that we do, the critical part of this, the processing that we do before the row, before the recursion, is what we're going to say is the spot that we put the queen in, the diagonal to the left and the diagonal to the right downwards from that position, we're going to increment each of the row vectors there by 1. And we're also going to straight down the row there as well. We're going to increment. So there's going to be a diagonal, left diagonal, right diagonal. So LDAG, RDAG, and then just row or just column. So LDAG, RDAG, and column. And we're going to modify each of those values for each row down from the current row position. And we're going to update our state to add 1, meaning that this queen is guarding all of those positions. So the number of queens guarding those positions increases by 1 if there are any. And if those were negative ones, then they would just jump to a 1, I guess. So it only increments the ones that are already non-zero by 1, and the ones that are negative, then we update them to a 1. The negative ones are just going to mean that nothing is there. There's not a queen, and there's no queen guarding it or anything like that. Anything other than a 0 means there's no queen. That's the idea. So we can actually do it the other way around. We can actually say the zeros will drop them to -1. That might be better. Yeah. So then the next row, obviously that's going to modify that particular row that we're looking at. Only the zeros we can put a queen at, or only the zeros we could put a queen at, and then we flip that to a -1 and then update. When we reverse, we do the same operation but decrement all of those numbers from 1s back to 0. Yeah, I think zeros should be what we use if we could put a queen there or not, and then we'll just make it a -1 to denote that there's a queen there. I think that's a simpler way of doing it. So that's how we're going to code this up. It should be relatively straightforward. The difference between this one and the next one, obviously, is that we don't actually need to convert the board state. Excuse me. Once we end, the number of rows is just going to be n. I think total number of rows we need. So once we get to the once we've placed all the queens, then that's a solution. Then we can just record it. So yeah, in the other solution, the next one we're going to write, the only difference is going to be just the base case when we record our solution. Instead of converting to an array of strings for the board state and pushing that to our return vector, we're just going to increment our return value by 1 just to say that we got another solution. That's it. And that's it. So this is how we're going to do it. So we're going to say we have our return vector. So look at this. Look at this thing. Ret, and we're going to say auto DFS or recurse, however you want to express it. It's really a DFS. We're going to DFS and return ret. Ret is going to be here. We're going to say constant row and also state. We're going to say standard vector of ints row, or just say state for each row. And we're going to say we said base cases, base case if row is greater than or equal to n, then we're going to yes, I think that's fine. If it's greater than or equal to n, then we have our convert the state to an array of strings, a vector of strings. Add the vector to the return value, return vector, and here you just return. There's nothing to return, just void. Here we're going to say there's a loop, so we're going to say for it's going to be like this. So it's going to be int I equals 0, I is less than. You actually can say const int x it's going to be the state for this particular row. We're going to say if x is actually equal to 0. Then we can do the following things. Yeah, I think it's fine. Yeah. So we're going to modify. So we're going to say, actually, yeah, I did this wrong. Huh. Yeah, that's kind of interesting. Yeah, we do want to do something like this. And I'll explain in a second here. If x is 0, state row I equals -1. We're going to recurse, update this back to 0. The recursion is going to be row plus 1 f. I think it's that simple. And the initial row is 0. And what we're going to do is for ints, it's not column, but it's really well x, that's fine. So we could say, really I is a column, yeah, it's really what should be C. Int of, so we're going to have a diagonal, LDAG, diagonal, is going to be initially at C. Right diagonal is going to be at C. And we'll just say R is going to be equal to the row. And so left diagonal, right diagonal, and then column is going to be C. Or current column, current C is equal to C. Or just C. Actually, C is not going to change. I take that back. That's fine. These integers. So left diagonal, right diagonal starts off at C, and then R starts off at row. And we're going to say while row is R is less than n, you're going to increment the row. You're going to decrement LDAG, and then you're going to increment right dag. So there's the left diagonal, right diagonal, and we start off at C. And actually, we want them to start off at C minus 1 and C plus 1. And R is going to be start off at row plus 1. Yeah. And we're going to say if LDAG is greater than or equal to 0, then set state of row LDAG, dag, plus equal plus plus. Same thing here. If the right diagonal is less than or equal to n, or less than n, then increment that, and then say if, and then actually this is just state of, it's not row, it's R, we're going to say. State of R of C also increments. So we start off at row plus 1, and we should have less than n. Yeah, this is so update diagonals. So insert queen, update diagonals, recurse, remove the queen, and then remove diagonals. Remove add queen diagonals. Yeah, that's it. That's all we gotta do. And these are just, we decrement these. So all the things that we added, we just go in the same direction and remove them. Yeah, so these are all the things beneath the queen. Something like this is all you got to do, really. How about this? What happens if we do this? and then converting the state to a vector of strings and add the vector. So we'll just say for int r equals 0, r is less than n, plus plus r. So for each row, we're going to say a new string, so rs, and we'll say for it, we could just do const int x in row of r, or not row, state of that row, and we'll say if x is equal to -1, that's a queen. Otherwise, so we'll say rs plus equals q. Otherwise, rs plus equals a dot. I think that's all you need. And then you just have so you have a vector of strings, just say board, board dot pushback rs. So you build for that row, for each row you're going to build this string, and you're going to add that to the board, and then you're going to say ret dot pushback board, and that's all we need to do. And that's even not even returning anything, we just return here something like this. See if this compiles. Start with that. Runtime error. Reference binding to null pointer. Oh, interesting. Oh, I see. Yeah. So this is going to be n vectors of size int, size n, and initially 0. I think all of them. Yeah. Nice. There you go. This is a column. Yeah, each column in the row. Yeah. Okay. So I think that's it. So we'll just do 1 through 9 and see if we're right. And this is actually a case where you can actually test every test case, which is kind of neat. All the test cases they want, you can test it directly to see if you're right. I like that. 18 minutes it took us. Okay. All right, we're done. Got it. Easy peasy. So yeah, 8 milliseconds. Not the fastest. Could be faster. You could maybe do something with like we're using a bit of memory, and we're also you don't actually need to have all of these diagonals and things set up, but this works. So not the fastest, but oh, there we go. 4 milliseconds. Probably there's a way to do this using less memory, but we're not doing that. So a simple solution, straightforward solution. All right, I'm going to end it here. Say thank you for watching. It's been fun. I'll talk to you soon. Super simple, super straightforward, pretty quick to code. We're going to actually code. We're going to do the next n queens 2 problem. Just copy paste the code basically, and then we'll do another problem after this because this one's pretty quick. So yeah, thanks for watching. Take care. Talk to you soon.